This video introduces equivalence relations. A relation R on a set A is called an equivalence relation if R is reflexive, symmetric, and transitive. Let's look at an example. Let's let R be the relation on a set of non-zero real numbers given by A is related to B if A over B is rational. Note that we're looking at non-zero real numbers, so we don't have to worry about dividing by zero. Let's check if R is an equivalence relation. First, let's check if R is reflexive. So we need to check for all real numbers x, non-zero real numbers, is it true that x is related to x? i.e., is it true that x over x is a rational number? I'll write that as being an element of Q. Here, Q is the set of rational numbers. Well, remember, x is not 0, and so x over x is just 1, and that's definitely a rational number. So yes, it's reflexive. What about symmetric? Here we need to check for all x, y, non-zero real numbers. Does x related to y imply y is related to x? In other words, does x over y being a rational number imply that y over x is a rational number? Well, yes, it does, because the reciprocal of a non-zero rational number is also rational. In other words, if x over y is equal to p over q for some pq non-zero integers, then y over x is going to be equal to q over p for non-zero integers p and q. And so it will also be rational. Therefore, the relation is symmetric. What about transitive? To show that this relation is transitive, we want to show that if x, y, and z are non-zero real numbers, and x is related to y and y is related to z, then x is related to z. In other words, we want to show that if x over y is rational and y over z is rational, then x over z is rational. Well, this is true because x over z is equal to x over y times y over z. So if x over y and y over z are rational, then their product is also rational, since the product of two rational numbers is rational. So we've shown that this relation is reflexive, symmetric, and transitive, and therefore it is an equivalence relation. Let's try another example. This time, let's let tilde be the relation, again, on the set of non-zero real numbers, and this time A is related to B if A times B is rational. Is tilde also an equivalence relation? Let's check. First, we'll check reflexive. Is it true that for all non-zero real numbers, A is related to A? What this means is it true that A squared is always rational? This is the same thing because A related to A means that A times A is rational, which is the same thing as A squared being rational. But this does not always hold because, for example, pi is not rational, so the square root of pi squared is not going to be rational, and so the square root of pi is not related to itself, even though it's a non-zero real number. In fact, the square root of any irrational number won't be related to itself. So our relation is not reflexive, and we already know that it's not an equivalence relation. But just for completeness or just for fun, I'm going to go through the other two properties, symmetric and transitive, just to see if either of them holds. As far as symmetric, we need to check that for all x, y non-zero real numbers, that A related to B implies B related to A, i.e. does A times B being a rational number imply that B times A is a rational number? Well, that's definitely true because A times B and B times A are the same number. So this relation is symmetric. Let's check about transitive. Transitive says for all x, y, z in my set, we want to show transitive, we want to show that if x is related to y and y is related to z, then x is related to z. So that says if x times y is rational and y times z is rational, then x times z is rational. Maybe pause the video for a minute and try to prove this or find a counterexample. In fact, this is not true. For example, let x be the sixth root of 2, let y be, say, 5 over the sixth root of 2, and let z be the sixth root of 2 again. Then x times y is the sixth root of 2 times 5 over the sixth root of 2, which is 5, which is a rational number. Fine enough. And y times z is also a rational number. But x times z is 2 to the 1/6 times 2 to the 1/6, which is 2 to the 1/3, the cube root of 2, which is not a rational number. So this relation, while it's symmetric, it's not reflexive and it's not transitive. So it's not an equivalence relation. In this video, we defined equivalence relation to be a relation that is reflexive, symmetric, and transitive. We saw one example of relation that satisfied all those properties and one example that did not.